In the next part of today's lecture, we're going to introduce our first reinforcement learning algorithm, which is called policy gradients. Now, there's going to be quite a bit of algebra and calculus in this part of the lecture. It's going to be, a bit mathy. Probably this is going to be the most mathy part of the course. The math is not that complicated, but there's kind of a lot of it. So if some of it is unclear to you, consider rewatching that part of the lecture a second time to work through the math. For me, something that often helps is to work through it on my own on a piece of paper after learning about it. So try to be patient with this part of the course. There is a fair bit of math. It's not very difficult math overall, but it might be a little dense, and it might take you a little while to fully understand it. Okay, so this is the reinforcement learning objective that we saw in part 1. You want to maximize the expected value of the sum of rewards over all time in expectation under the trajectory distribution induced by the current MDP and your policy pi theta at given st. So let's start with a little warm-up. How can we evaluate this objective? So let's not worry about actually optimizing this objective, although that's what we're ultimately going to want to do. Let's first ask, how can we evaluate this objective? So if I give you a policy pi theta, I hand you a neural net, how can you estimate its expected reward? Right? You can't enumerate all possible trajectories and sum over them because there are exponentially many of them. The number of possible trajectories increases exponentially in the time horizon. But you can construct an unbiased estimator. You can guess on your own how to do that, and then continue the lecture to see the answer. So the answer is to construct an unbiased estimator, and we'll call this quantity j of theta for convenience. All you have to do is generate samples. So you can approximate it as a sample average. We're going to run the policy n times to generate n sample trajectories from p theta of tau. We'll sum up the rewards along each of those trajectories, and then we'll average them together over the trajectories, and that is an unbiased estimator for this expected value. So this is always true. If you have an expected value of some function under some distribution, you can sample from that distribution and then average together the values of the function at those samples, and that is an unbiased estimator for an expected value. So sampling from the trajectory distribution literally means running the policy in the real world. So when you run the policy in the real world, your assumption, your MDP assumption, is that that process works as follows. Sample an initial state from P of S1, and then sample each successive state from P of St plus 1 given ST AT. So those samples come exactly from the distribution P theta tau if you take your actions according to pi theta. So you would literally run the policy multiple times, compute the expected reward of each of those trials, and then average them together. So the idea behind the first reinforcement learning algorithm that we'll learn about, which is policy gradients, is that we can use the same sample-wise estimator with some modifications to compute the derivative of this expected value. And if we compute the derivative, then we can use our favorite gradient-based optimization algorithms to maximize the expected reward. So this is basically going to be gradient descent for policies, except now, since we're maximizing the objective, it's actually gradient ascent instead of descent because we want to make the rewards big, not small. But you can always flip the sign and make it descent. It's the same thing. Okay, so what we need is the gradient. All right, so now we'll work through a clever mathematical trick that we can use to evaluate the gradient of an expected value with respect to the distribution for which we're computing the expectation. So I'm going to use R of tau as shorthand to denote the sum of rewards, just so that the notation doesn't get too cluttered. And by the way, there's a little bit of a notational snafu on the slide. P of theta of tau and pi of theta of tau are exactly the same thing. It's just, I just accidentally used the wrong symbol, but they mean the same thing. Okay, so you can write out the expectation as an integral, or a sum if you have discrete states and actions. But here I assume continuous, so I'll write it as an integral. So the expected value of R of tau under pi theta of tau is just the integral over all taus of pi theta tau times R of tau. Now I'm going to want to compute the gradient of this thing with respect to theta. Now, the gradient operator is a linear operator, so it actually commutes with the integration sign. So that means that the gradient of the integral is the integral of the gradient. Okay? We're not there yet, though, because, well, computing grad theta of pi theta tau is not very easy. So here's a convenient identity that we can use. If you have pi theta tau times the gradient of log pi theta tau, you can apply the standard formula for the derivative of a logarithm, and that turns into pi theta tau grad pi theta tau divided by pi theta tau. That's because if you take the derivative of log of f of x with respect to x, that's just 1 over f of x. So that's where, well, it's 1 over f of x times df dx. So that's where you get this formula. But now you'll notice that pi theta tau in the denominator actually cancels with the other pi theta tau, and that just leaves you with grad theta pi theta tau. And what we're going to do is we're going to apply this identity in reverse, right? So this tells us that pi theta tau grad log pi theta tau is equal to grad pi theta tau. And we've got a grad pi theta tau inside our integral, so we'll actually replace it with the left-hand side of this convenient identity. Okay? And that will give us the integral over all tau of pi theta tau grad log pi theta tau times r tau. Now, why did we want to do this? Well, the reason we wanted to do this is because now we again have an integral of some quantity times pi theta tau. And that is an expected value under pi theta tau. And this is very important because we know how to estimate expected values. So calculating some arbitrary integral, like the integral of grad theta pi theta tau times r tau, is difficult. Computing an expected value, or at least approximating it with samples, is very easy. So we would really like to have an expected value under pi theta tau, and that's what we've got. So before, if we wanted to evaluate how good the policy was, we would sample from pi theta tau and average together the rewards. Now, if we want to compute the gradient, we can sample from pi theta tau and average together grad log pi times r tau. Okay. We're not quite done yet, though, because we don't actually know how to calculate grad theta log pi theta tau. So let's work through how to do that. Here's the equation for pi theta tau. Remember, tau is just a sequence of states and actions, and that's just a product of a bunch of different probability terms. And we're going to take the logarithm of that. Okay, so if we take the log of both sides, log pi theta tau is equal to log of p of s1 plus sum over all time steps of log pi theta plus log of the transition probabilities. Remember, when you take the logarithm of a product, you get a sum of logarithms. Okay, so that's what this part is equal to. Now we're going to take the derivative of this with respect to theta. Okay, so this is log pi theta tau, and we're taking the derivative with respect to theta. But remember that when you take the derivative of a sum, that's the same as taking a sum of derivatives, because a derivative is a linear operator. And what you can see here is that the only term inside that sum that depends on theta is log pi theta. The initial state probabilities and the transition probabilities do not depend on theta. And that's very, very important because those terms are not terms that we know. Like, we know pi theta, at given st, because that's our neural network. But we don't know p of s1 or p of st plus 1 given st at. Those are determined by the universe, by nature. So it's very good that their derivatives with respect to theta are 0, because that means that we don't need to know what they are. Because regardless of what they are, since they don't depend on theta, their derivatives will always be 0. And that means that we can simplify our formula for the policy gradient into something that we can actually compute. All we're left with is the sum of these log pi theta at given st terms, which means that the full policy gradient is an expected value under pi theta of tau of the sum over all the time steps of grad log pi theta at given st times the sum over all time steps of the reward. And all of those quantities are quantities we can compute at samples sampled from pi theta tau. So if you want to evaluate the policy gradient, all you have to do is generate some samples from pi theta tau, which you get by just running your policy in the world. And for each of those samples, calculate the grad log pi at given st and the r of st at every time step and multiply them together. So this is the formula for the policy gradient, estimated with samples, and all these terms can be calculated. So this is a formula that you can actually implement in a computer, provided you are allowed to sample new trajectories by running the policy in the world. And then once you've computed this gradient, you just do gradient ascent, which is basically just gradient descent with the opposite sign, with a plus sign instead of a minus sign. So this approach to reinforcement learning is, it's a very classic algorithm sometimes called reinforce. It basically consists of 3 steps: generate samples by running the policy, sum up the rewards along all of your samples, so basically estimate the return. You can think of it as a model. It's a very, very naive model, just a summation of all the rewards, and then improve the policy by applying the gradient. And this is called the reinforce algorithm sometimes. So the classic Williams 1992 paper calls this reinforce. Just 3 steps: sample trajectories by running your policy, evaluate the gradient using those samples, and then perform a gradient ascent step. So this is reinforce or policy gradient, sometimes also called likelihood ratio policy gradient. So that's the basic idea. But let's kind of unpack this method a little bit more. So first, what is this grad log pi thing? Well, pi is the distribution given by your neural network. So if you have discrete actions, pi of a given s is just the result of the softmax. So you can compute these gradients using backpropagation in your neural net. That's actually pretty straightforward. In fact, this gradient is superficially quite similar to the maximum likelihood gradient, the one that we actually used to train with supervised learning. Mathematically, this insight is not particularly deep, but implementation-wise, it's actually very important because it suggests that we can implement the policy gradient in a way that is not too different from how we implemented regular supervised backpropagation. So if you have supervised learning like we had before, imitation learning, then you would have the maximum likelihood objective. So grad theta j theta, that's the policy gradient, j theta jml, that's the maximum likelihood gradient. And if you look at these side by side, you can see that the only difference is that the policy gradient is multiplied by the reward, whereas the maximum likelihood gradient is not. And again, that is not mathematically a very deep observation because these things are, these 2 gradients are doing completely different things mathematically, but implementation-wise, it's a very useful observation because it suggests that we can implement the policy gradient with a relatively small modification on the maximum likelihood gradient. All we have to do is multiply our gradients by the total reward along that trajectory. Okay, we'll come back to this point in a second. But let's first build a little bit more intuition about the policy gradient algorithm. So, those of you that were following the math hopefully understood why this is the correct expression for the gradient of the reinforcement learning objective, but it may be a little bit opaque. You might be asking like, okay, well, we did a bunch of algebra and we got an equation. What does it actually do? What is the intuition behind why this algorithm is a good idea, why this algorithm will increase our expected reward? And actually, the policy gradient method does have a fairly natural interpretation. So to avoid all the parentheses, let's just simplify things a little bit. Let's just write it like this, where we have pi theta of tau I and r of tau I, so that just hides the sum inside this tau notation. Okay? And let's compare it side by side with maximum likelihood some more. So maximum likelihood increases the probability of all the actions along the trajectory, whereas policy gradient increases the probability of actions along trajectories of positive reward and decreases the probability for trajectories with negative reward. So if you run your policy and some of your trajectories are really good and have huge reward, some of your trajectories are really bad and they have very negative reward, what policy gradient will do is it'll try to make the actions along the trajectories with the large rewards bigger, and it will try to make the probabilities for the actions along trajectories with low rewards smaller. And that should improve your policy because you're making the good stuff more likely and the bad stuff less likely. So good stuff is made more likely, bad stuff is made less likely. This is essentially a mathematical formalization of trial and error learning. So even though it's a gradient-based algorithm, what it actually does in practice is it just makes good stuff more likely and bad stuff less likely. Very much in line with what our intuition would say is the right strategy if you want to learn by trial and error. Okay, let me briefly remark on how policy gradient handles partial observability. So I mentioned in the beginning of the lecture in part 1 that we would set aside partial observability for now. Policy gradient is one of the few reinforcement learning algorithms that doesn't care whether you have partial observability or full observability. Many variants of policy gradient, like actor-critic methods, do care, but regular vanilla policy gradient is one of the few algorithms that does not care, which means that if you have a partially observed problem, you can just plug in those observations into your policy and nothing about the algorithm needs to change. That's because the Markov property is not actually used by the policy gradient algorithm as I've described it so far. Now, there are other variants on policy gradients that we'll learn about later, like actor-critic, that do use the Markov property, and there great care must be taken when handling partial observability. But the regular policy gradient that we've discussed so far does not use the Markov property, which means that it does not care whether your state is Markovian or not, which means that if you have observations, just plug them right in and nothing needs to change. But this is only true for the regular policy gradient method.